Alright, welcome. In this video we're going to discuss the graph of the tangent function, and remember that tangent we can define as sine over cosine. So in terms of thinking about the domain, remember the domain is the numbers we're allowed to plug in. That would mean what angles are we allowed to plug in, and we treat numbers or angles in radians as equivalent to real numbers. Looking at this ratio, we got sine over cosine. Well, we can't divide by 0, so that would bring up the question, when is cosine equal to 0? All right, we know from our work that that happens at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. All right, so those angles we can't plug in, so the domain is going to be all angles not equal to pi over 2, 3 pi over 2, 5 pi over 2, so on, and then negative pi over 2, negative 3 pi over 2, etc. All right, now we could generalize this. We want to write them all down at one time. What are we looking at? We're looking at odd multiples of pi over 2, and we could express this way, 2n plus 1 over 2 times pi. All right, that's a fancy way to write it down, but anyways, it's just odd multiples of pi over 2. Not even multiples, just odd multiples. All right, so those are the values that we can't plug in, so theta can't be those. What does that imply for the graph? We're going to look at that in a second. It's going to turn out that we're going to have vertical asymptotes at these values. Okay, an asymptote, as we're going to talk about, is a line where the graph gets closer and closer to as x gets closer and closer to that value. All right, so we're going to have vertical asymptotes at all of these odd multiples of pi over 2. All right, we're going to see that in the graph. All right, another way for us to visualize and think about the graph, all right, and kind of understand why the graph looks the way it does, is to remember that tangent is equal to sine over cosine, which in terms of the unit circle is y over x. Now, if we take the equation y over x equals tangent of theta, and if we multiply both sides by x to clear the fractions out, then we get this statement here that y is equal to tangent of theta times x. Now, remembering our knowledge about linear functions, where we have y equals mx plus b, we know the coefficient in front of x is the slope of that line. All right, now our value for b here would be 0. All right, so what we're really referencing here is this graphical interpretation that the tangent of the angle theta is really the slope of the terminal side of the angle theta. All right, and then we're going to look at how that can help us understand the graph. All right, so let's go over to Desmos and do a little investigation here. All right, now I've got this slider, and I've got this up here for reference. Tangent is sine over cosine. I've got sine over cosine here, and right now it's at 0. The angle t is at 0. It's plotted here. All right, 0 radians. Now, what happens when we increase that? We're seeing a couple of things. We can see the angle drawn there. Tangent, we're not graphing the tangent function quite yet. We can see the value of the slope, which is equal to tangent. All right, and we can see that's a positive slope for that angle right there. What happens as we keep increasing the angle? Well, we can see the value is getting larger for the tangent function, which again is the slope of the terminal side of this angle. As we get closer and closer to pi over 2, which is 90 degrees, this is going to get to be a steeper and steeper angle, steeper line, if we will, and therefore the slope is going to get larger and larger. But when we go to vertical, all right, we go right at pi over 2, that's undefined because we can't talk about the slope of a vertical line. All right, so in the first quadrant, for angles, acute angles in the first quadrant, right, tangent of 0 is 0 because the slope of that angle is 0. For angles that are acute, we're going to have a positive output value for the tangent function. If we go backwards, then we can see in this figure the slope of this angle for this negative angle, the slope of the terminal side of this angle will be negative, and we see that the value for tangent is coming out negative. The closer we get to pi over 2, the steeper the line gets with a negative slope, the steeper the terminal side of that angle gets with a negative angle, and therefore our value for tangent is more negative. It's larger in magnitude, but negative. If we go at pi over 2, I passed it, negative pi over 2, excuse me, then we can see again the tangent function's undefined there. All right, if we went past that again, then, or past that, and we could see we'd have a positive slope. Now notice here, the angle is negative 2.18 radians, but the value for tangent is positive because the slope of the terminal side is positive. We'll go forward just a little bit more here. We'll stop right there. Right there, that's negative 135 degrees, or negative 3 pi over 4 radians. That's that angle drawn down here. Now notice if I have this dashed line, if we extend the terminal side of that angle back through the first quadrant, we're talking about a 45 degree angle there. The slope of this line is slope 1. It's the line y equals x. The output of tangent is that slope, which is just 1. All right, but this is showcasing us something. I'm going to focus on this 1 here for a minute. If I go at negative 135 degrees, that's the same output value for tangent that we will get if we go to 45 degrees. All right, so, because the slope of that line is 1. If I go 180 degree revolution to go to 135 degrees, again, our angle is different, but the slope of the terminal side, or the slope of the line through the terminal side of our angle, is still 1. All right, so what's that showing us? That the period of the tangent function is not 2 pi, but just 180 degrees, or pi. All right, so let's make note of that. How can that help us think about the graph? We just illustrated that. How does it help us understand or think about the period of the tangent function? We can see that the period for tangent is equal to pi. All right, when we talked about solving certain trig equations using inverse tangent, we had to sometimes make adjustments by adding pi to our angle that we got with the graphing calculator. That has to deal with the period of the tangent function. All right, now let's actually go back and look at the graph, and I've got another Desmos visual for us. Okay, now in this one, I do have the graph of this is what the tangent function looks like. Now let's understand that. Again, what I'm going to do is move this slider here for t, and as t goes forward, all right, now this is, we're trying to plot in the coordinate plane, in the xy plane, y equals tangent of x. So x is on our horizontal axis. That stands for your angle in radians. Now what I've drawn here is just at that x value, I've drawn the slope of that angle. Or I've drawn that angle, I should say. So this is the angle that's kind of pushed over to that x. All right, so there's your angle, x radians, drawn, kind of a line segment representing that. Now the slope is positive there. The slope is equal to, as we showed, the value for tangent, and so we're up at this positive height. As we increase and get closer to pi over 2, this slope of this terminal side of this angle will get steeper and steeper, and that's going to make this point on the graph go higher and higher and higher. All right, we can't, as we illustrated a bit ago, we don't have a slope right at pi over 2, and that's why we have these vertical asymptotes here. Now going left of 0, again, that would correspond to a negative angle that's drawn here. So x is, t and x are corresponding with one another there. All right, so capital T is playing the role of x here. That's our angle. All right, so if we have a negative angle, like negative 0.69, then that's going to be drawn this way. All right, and I just shifted it over for illustration. Right below that point, we're going to graph the value of tangent. Well, that's the slope of the terminal side, and that slope is negative, and therefore the point on the graph has to be below the x-axis. It's down here. The closer we get to negative pi over 2, the more that point's going to go down, because this angle is getting steeper and steeper, more negative. All right, so that point goes down. So we go to the right. Close to pi over 2, the graph goes up, and the closer and closer we get, the higher and higher it gets. All right, and that's why we have these vertical asymptotes there. So hopefully that's a good visual to help us understand the graph. We can see that the period is from pi radians. It's going to show up in these chunks between negative pi over 2 and pi over 2. The next cycle of it will be between pi over 2 and 3 pi over 2. and then that pattern just kind of repeats itself going forward and backwards. All right, but if we zoom out here, we see that the graph, I'm just going to now kind of click on the graph and trace it, gets closer and closer to that line without quite ever touching it. So if I want to go way up and trace on that red graph, oh, I'm on the wrong one, try to go over to the other one. There we go, I'm on the red one, so I'm getting closer and closer, but we're not quite getting to 1.57, which would be pi over 2, but my y value is getting higher and higher. All right, and again, that's what we refer to as a vertical asymptote. I'm just going to zoom back in, and that's our pattern for the tangent function. All right, so we got vertical asymptotes. Our graph gets arbitrarily close to but doesn't touch at pi over 2 and negative pi over 2.